Okay, our project is about machine learning.
So as machine learning becomes more important in society, we've got more concerned about the information that's used in training. So while people can delete their information from websites and databases, you can't really delete your data from a machine learning model. So machine learning aims to allow models to forget certain samples while remembering the stuff they learned from the rest of the data. This has applications in user privacy, reducing bias, and fixing incorrect training.
So in this project, we hope to make an unlearning model, an algorithm based on previous implementations. More specifically, we're going to train the model on the UTK dataset to predict age from a face, and we're going to attempt to unlearn it successfully. We're also going to submit it to Neuro IPS machine learning challenge. Our dataset consists of pixels and ages. Our inputs will be the pixels and the output will be the ages. And we normalize the data and duplicate it across two channels to resemble RGB.
This is just some sample images from. All right, so the first model that we attempted to do unlearning on is the ResNet 18 architecture with pre-trained weights on ImageNet. And what we did was we froze the first 5 residual blocks, we trained the rest, and then we added an additional regression layer that was just a linear layer. And then we did some train test splits, 90% training, 10% testing, and then these are some of our other hyperparameters. So for this, we had 3 unlearning methods. The first one is basically retraining just on the retained set so that it has never seen the data that we need to forget on. This is impractical in the real world because it requires retraining the entire model. The other is EUK, exact unlearning the last K layers, where we basically reinitialize the last K layers and then retrain that on the retained set. We also have fine-tuning on the last K layers, where we just take the train model and then we just further train on the retained set without reinitializing the weights.
We then explored selective synaptic dampening, or SSD. This is based on the idea of looking at the weights importance in the forget set and the rest of the train set. If it is important to the forget set, but unimportant to the train set relatively, then we dampen that weight. This is all using the Fisher information matrix to determine that importance. And we also have the hyperparameters, selection threshold, and damping factor for us to tune. The main benefit to using SSD is that it's fast and it doesn't need to retrain. We then explored the idea of combining SSD and fine-tuning into SSDFT. We first freeze our layers, K layers, and then we run SSD on it, and then we fine-tune it. We call this a DF block, or a dampening and fine-tuning block. Then we try chaining these DF blocks and altering the hyperparameters. We realized that it's better to go less aggressive dampening and less specific fine-tuning, so we can have different layers similar to a neural network. We also explored age classification with SSD. This is because SSD and also the NeurIPS competition was originally designed for classification. We split this into 2 tasks: class unlearning, which is unlearning all the data from a single class, and also random unlearning, which is unlearning random data points. For this, we used a modified pre-trained ResNet, and similar to before, we replaced some layers to simplify it. This is just a table describing all the changes we made. We basically edited the later layers to make it simpler and changed the 1000 dimension fully connected layer to 9.
All right, now we're going to go over some of our unlearning results.
Okay, so results. Our goal was to make an algorithm that will run in a fraction of the time it takes to retrain the model, but achieves a similar effect. So the things to consider: the accuracy. The unlearned model should have similar or better accuracy on the retained and test sets as the retrained model, and the forgetting quality. So how we'll measure that is the failure rate of membership inference attacks, which attempt to infer if a model was trained on a piece of data. If we successfully mimic a retrained model, these attacks should fail. So how the membership inference attack works is we're going to train the logistic regression on the validation losses and the forget losses and have it attempt to tell them apart. If it succeeds, it means unlearning failed because it's possible to differentiate the sets by loss. If it fails, it means unlearning succeeded because the loss distribution for valid/forget are similar.
So running the membership inference attack on the model that did not have any forgetting at all, we see the attack accuracy is 0.74, which means it's very easy to discern which data points were trained were in the initial training set versus which ones weren't. And remember, MIA works by looking at the losses of the data points and then trying to predict that if it was seen in the original training data or if it wasn't. Now, when we retrain the model from scratch on just the retained data points, we see that, first of all, the training loss of the forget set and the validation set are identical, which makes sense because the model has never seen the forget set, and the attack accuracy is random, which means that it is impossible to discern the forget set from the validation sets. This is basically the best case scenario, but it requires retraining the model from scratch, which is infeasible.
So our first thing, we fine-tuned the last K layers. When the membership inference attack rate dropped from 74% to 69.8%, we had K equals 5, 90 epochs with a learning rate of 1/1000th. We explored other Ks, but the effects were similar. So this shows good signs of forgetting. A larger K lets more of the model fit the retained set, but very large Ks would take more compute and potentially overfit the retained set. So here you can see the loss distributions. Initially, the attack accuracy goes up after 30 epochs. You can see it's 0.813 when it was really 0.74. But after going to 90 epochs, unlearning works and the attack accuracy drops to 0.698. Then we tried to just reinitializing the last K and then optimizing them. And for that, the membership inference attack went from 74% success to 66.4 success. Again, K equals 5, 30 epochs, learning rate 1/1000. Here you can see the loss distribution graph. You can see the forget set is like almost the test set. It's almost there, but not as good as fully retrained. Okay. Here's a table of our results for all the algorithms we mentioned so far.
For SSD, we realized that regression resulted in very little change in the model weights. We believe this is because SSD is designed for classification problems, so here we focus on the classification tasks. As an overview, we find that class unlearning is easy for SSD and random unlearning is hard for SSD, and we'll look into trying to combine SSD with fine-tuning. So this is an example of class unlearning on the first class, age 0 to 6. Our goal is to try to make the accuracy for the forget set as low as possible in this case, because we want to completely unlearn that whole class. Here, SSD is able to do that, and it's also able to keep the retain very high, so we consider this XSX. So here are the confusion matrices from before SSD for the train set and test set, and here are the confusion matrices after running SSD. For random unlearning, you can see that there's very little change in forget and retain in our original SSD. We also tried a more aggressive SSD with different parameters, and this just resulted in worse accuracy overall. Then in our new approach, we realized that 3 DF blocks was the ideal, and this showed very promising results. Additional DF blocks either overfit the model or forget too much, and inclusion SSDFT combines the speed and the forgetting potential of SSD and also the retained potential of fine-tuning.
So overall, none of the unlearning methods were able to unlearn on their own. The last K methods retained accuracy, but didn't do much for MIA attacks. And SSD does well on class unlearning, so on forgetting a class, poorly on just random forget set. So by combining SSD and fine-tuning, it's fast and it produces good unlearning results, and we hope to experiment with the DF blocks and similar techniques in the future.
References.